All right, let's start. I'm very happy to have Ryan Williams from Boston University at the top. The title is Higher Segal Sugawara.
That's exceptional.
Exceptional symmetry.
Yes.
And fivebranes. Take it away.
Thanks so much for inviting me to speak. It's lovely. One of my favorite places. I really appreciate it. It's great to be here. As Tom said, my title is Higher Sugawara Exceptional Symmetry in Five. So this talk sort of surveys two main parts of my research program as of late, which maybe I'll just say briefly what those are right now. The first is to develop mathematical technology which handles higher dimensional quantum field theory in much the same way we use vertex algebras to handle conformal field theory. So sort of extending all of the powerful techniques we have as mathematicians to understand two-dimensional conformal field theory to higher dimensions. And this doesn't work for a generic quantum field theory in higher dimensions, but for a particular type of quantum field theories, those which are holomorphic, the sort of methods can be generalized to some extent. So part of the talk is sort of touches with this research program. The other program is to more example driven. It's to really come up with a mathematical definition / understanding of at least a part of this ubiquitous six-dimensional superconformal field theory. And there's a lot of overlap between these two programs in my eyes at least. But those are really the two sort of programs that I'll touch on. So as is no surprise in conformal field theory, one of the universal objects is this Virasoro-Lie algebra. So that's where we're going to start our life today. As many of you all know, the Virasoro-Lie algebra, it's a central extension of the Lie algebra of vector fields on the punctured disk. And in fact, it's the unique non-trivial central extension of that Lie algebra. This of course plays a very important role in conformal field theory in the sense that it's the universal symmetry of a conformal field theory. Anything that should be called a conformal field theory has a symmetry by this Lie algebra. That's almost just a definition. This talks about a generalization or enhancement of this Lie algebra of symmetries of a conformal field theory. And this enhancement will be universal in a very similar sense to not two-dimensional conformal field theories, but this time six-dimensional n equals 2, 0 superconformal field theories. So it plays a parallel role to the Virasoro, the symmetry that I'll talk about plays a parallel role to the Virasoro-Lie algebra, but for these six-dimensional 2, 0 theories. And of course, for this talk, everything that I say is at the level of the holomorphic twist. So this is a simplification of the six-dimensional theory that I always get this wrong. This would be called an eighth BPS in this dimension, or quarter BPS. I get it wrong all the time. It's the we have I guess we have 16 here. Yeah.
You won't preserve all.
We don't preserve all 16. Yeah, I think we only preserve. I think these are quarter BPS. Yeah, so this is a strictly more interesting twist than the one which is typically studied in the context of the correspondence of AGT, which studies the more topological twist, the half BPS operators in that 6D theory. So the next part of this talk will be about sort of an enhancement of this of pieces of this AGT correspondence, which you can gather from this from our understanding of this richer twist of the six-dimensional theory. And under this correspondence, we'll see that this symmetry algebra that I'm gesturing at exactly does play the role of the Virasoro, or becomes the Virasoro. From there, I'll also discuss some enhancements of AGT, which makes sense for this holomorphic twist. Cool. So I want to start with this higher dimensional Sugawara. So nothing about fivebranes in the first part of this talk. This is all going to be sort of enhancements of familiar structures that everyone has seen in conformal field theory. So I'll start with the very basic conformal field theory. It's called the chiral boson. conformal field theory. So this is described by a single field, generated by a single field. It has spin 1, conformal weight 1, with the following OPE. So here the field I'm calling B. So it's very simple quadratic OPE. Importantly for me is that this vertex algebra actually doesn't have just a unique conformal structure, it has a family of conformal structures, family of stress tensors, which is labeled by a complex parameter lambda. There's sort of a universal part of the stress tensor, though, which is quadratic in the field B. So that's the typical stress tensor you're used to seeing in the setting of the chiral boson. With just the standard stress tensor, the central charge of this chiral boson is just 1. Turning on this deformation of the stress tensor changes the central charge. There's a way to express this in a more invariant way, this whole setup here. So one way to think about the field B, it's not actually a function, it's actually a holomorphic one form on the curve where the conformal field theory lives. So being holomorphic one form means that, well, in the language of differential forms, it means I'm a differential form of type 1, 0, and I am Dolbeault closed. So one thing that will be a recurring theme for me is that I never like to study equations. I just like to resolve them by cochain complexes. So I don't want to study this equation here. I actually resolve this condition here. So the more invariant way to think about this field theory is that the field B is actually a 1, star form on the surface, on the Riemann surface. Where by 1, star forms, I mean this entire cochain complex. So there's stuff in degree 0 and stuff in degree 1, potentially. The sort of physical fields all live in degree 0. And in cohomology, we're exactly imposing the condition or constraint that the field is holomorphic, namely Dolbeault closed. Oh, that's just a typo. Thanks. Yeah. It's 1, 0 and 1, 1. Thanks. Yeah. Okay. So the reason I'm setting it up this way, I'm trying to express this chiral boson as classical field theory, this classical space of fields that I can quantize. Where does the sort of need for this classical field theory, where do you see that it wants to be quantized? What sort of semi-classical structure is around? In the setting that I'm working in, the sort of semi-classical structure that's around is what physicists call the Batalin-Votkovitsky formalism. And it turns out that once I look at this complex, which resolves the condition that this one form be holomorphic, this space of fields has what's called a one-shifted Poisson structure. And this is really the analog, or this is sort of like a universal version of the phase space in a classical mechanics system being Poisson. And I'm going to go through this in the next few slides, what I mean by that. But let me just set up some analogies here just for a moment. So in classical mechanics or quantum mechanics, this sort of more typical picture, what we start with is a Poisson algebra, and we think about this as functions on the phase space in some classical mechanics system. And we can ask to quantize it, that is to find a associative algebra over the formal disk such that at the special point h bar goes to 0, we exactly recover this Poisson algebra. And the way you recover this Poisson algebra, namely the way you recover the bracket, is by looking at the commutator, taking h bar to go to 0. So this is this picture of deformation quantization of quantum mechanics. So the Batalin-Votkovitsky formalism shares many parallels with this setup here. So the thing that I start with classically is not a Poisson algebra, but it's one of these shifted Poisson algebras here. So I said above, this is such an example of a shifted Poisson object. I didn't say exactly what the Poisson structure was. Let me say what that is really quickly. So this is a linear Poisson structure. So it's just given by, linear in the sense that 1, star forms, that's a vector space. It's a cochain complex, but it's a linear object. And the Poisson structure is going to just be a bivector on that vector space. Okay. So it's some symmetric element of the tensor square of the space here. I can apply Serre duality to understand such an element here instead as a map from the dual of 1, star forms, which by Serre duality is 0, star forms, to 1, star forms here. And in fact, there's a natural operator that's called the holomorphic de Rham operator. So the semi-classical structure in the chiral boson, in this sense, is exactly given by this holomorphic de Rham operator. And the thing that I'm going to sort of try to explain in the next few slides is that quantizing this shifted Poisson structure is what gives the chiral boson vertex algebra, what produces the chiral boson vertex algebra in a precise sense. So how does that go? So you start with a shifted Poisson algebra from before, and you ask to deform it, just like we did in the quantum mechanics case. You ask if it's possible to deform this. Now, what sort of object are you deforming it to? It's no longer an associative algebra. What plays the role of an associative algebra here is the name, hence the name is a Batalin-Volkovitsky algebra. BV algebra, it's an algebra. It's actually a commutative algebra in this case, a graded commutative algebra. And somehow all of the interesting structure is in the form of a differential on this algebra here. So this is just a differential. So it's a degree 1 operator acting on A. And it has the property that it squares to 0. So just a differential. Importantly, though, this differential here is not a derivation for the product. So this is not a commutative DG algebra. It's just a graded algebra with this operator that's acting. There's some axioms that the structures have to satisfy that I don't want to get into. But the axioms say that when I take h bar to go to 0, I can recover this shifted Poisson bracket from this BV operator here. And that follows the following formula. So this is basically the axiom of a BV algebra. So if I have any two elements in my algebra, and I look at the following object here, let me not write h bar. Or, oh, I'm not going to get the signs right here, but so if we were in a commutative DG algebra world, this expression here would be 0 because the differential would just be a derivation for the product. What BV says is that it's not 0, but this combination here defines a bracket. And you can already see what why the degree of this bracket is not the usual thing in the Poisson algebra world, because this is a differential, it has degree 1. So this is why this bracket is also of degree 1. And it's essentially just the failure for this is called the BV Laplacian, it's the failure for this operator to be a derivation. Not in the way that I wrote it here, but no, not in the way that I wrote it here. I should, yeah, let me not write it with h bar right now. I'm going to mess it up. Yeah. So there's no h bar here, but it's akin to taking like the associated graded. So you can take the associated graded of a BV algebra without any h bar around and still get a shifted Poisson algebra by using this formula right here. I wanted to say one thing. Yeah, exactly. Yeah, that's right. The one thing I wanted to say is that actually in writing it this way, it's very parallel to the way a Poisson bracket comes from deformation quantization. This is exactly the failure for this product to be commutative, right? So this in this bracket here is the failure for this to be a derivation, which is also like a commutative structure. So in both sense, it's sort of probing deformation, but in slightly different ways. And you know, I could have. It looks like I just whipped this out of a hat. The right-hand side is highly motivated by physics, and it produces a lot of very sort of interesting quantizations. So let me move on. So I use BV quantization not just on its own, but in combination with the theory of factorization. And the factorization algebra is a way to codify the operators in a quantum field theory. So what happens is that sort of the way I like to think about field theory is that, classically, we have some maybe Lagrangian description, which we can easily define the operators of. This gives some factorization algebra. Coming from an action functional or coming from sort of semi-classical problem that we understand, we know that that factorization algebra has some bracket, has some extra structure, the semi-classical structure. And then I can ask to deform that. Or quantize that, and that's what I was trying to gesture at before. That's what the process of BV quantization is. So how does that play with factorization? So what is the factorization algebra? It's just an assignment, in part, of space, say a vector space or a cochain complex, could be any sort of thing, to every open set of your manifold. The way this recovers local operators is by taking the open set in your manifold to be very, very small. So it's not strictly the same thing as local operators, but if you take a limit over your open sets sort of containing a single point, that's going to recover the notion of a local operator at that point. But factorization algebra is more flexible in the sense that they take values on every open set, just like a sheaf. Unlike a sheaf, we don't have restriction maps. We actually have extension maps. So this is actually a covariant functor. It has to satisfy many axioms. So there's more data involved in a factorization algebra additionally. So the most important structure is that of a multiplication. That's why it's called an algebra. And the multiplication happens whenever you have the following configuration. So if you have a configuration, say, of two open sets in your manifold, which are disjoint, that's what this symbol means. So if you have two open sets which are disjoint, sitting inside of some bigger open set W, so this is U, V, and W, then you get a multiplication in the sense that you get a map from the tensor product of the value on those open sets, U and V, to the value on the big open set W. And I'm being a little sloppy here. I'm calling it a multiplication. There's actually many multiplications for every such configuration here. So this mu that I'm writing down depends explicitly on the embedding that I've chosen here. I'm not indicating that in the notation, but it does. So there's a lot of data involved in a factorization algebra, is all I'm saying. There's a lot that you have to prescribe. Oh, sorry, yeah, it depends just on the opens. Yeah, exactly. Just on it actually, but I haven't indicated that here, so yeah. So here's one of the main results of this program of Kevin Costello and Owen William, is that the observables of a classical field theory have the structure of a factorization algebra. And in fact, they actually have the structure of a P0 factorization algebra. That's one of these structures that I wrote down before, where we have a bracket of a shifted cohomological degree, this degree 1 bracket. And what this means is that for every open set, I can look at f of u, the value of the factorization algebra, and it has the structure of a P0 algebra. So open set by open set, it's a shifted Poisson algebra. Yeah, I should have said that earlier. So it's this sort of thing here. So it's a yeah, thanks. So here's a PN algebra so here, so this is just a commutative product. So that has nothing to do with the n at all, just commutative product. And 2 is that this is a degree 1 minus, and I always mix this up, n minus 1, thanks. Bracket. And by bracket, I mean it satisfies the version of the appropriate version of Jacobi. So you have a graded version of Jacobi. So you're right, when n equals 0, I'm getting back this thing here. So that means the bracket has degree minus 1. When n equals 1, I get back no shift at all. And indeed, this agrees with the notion of just a Poisson algebra. So over here, Poisson algebra is what I would have called P1 algebras in this terminology. Actually, for n bigger than 1, a Pn algebra is what you get by looking at the cohomology of observables in a topological field theory in dimension n. I'll say this in a minute. But Pn algebras in this sense are sort of a rigorous codification of Witten's version of descent, topological descent. They sort of encode the descent of operators in a TFT. It's sort of playing a universal role here. There's no TFT around. So somehow -1 shifted is like the universal thing. It's like a zero-dimensional quantum field theory in a sense. That's why I like the n being 0 there. But, so let me go back to this result of Costello and Williams. So observables of a classical field theory have a P0 factorization algebra structure, meaning their factorization algebras was want to be quantized in the sense of BV. Quantization, this may not be possible. So, unlike Koncevich's theorem on deformation quantization, any Poisson manifold can be deformed. This is not true for BV. So it's not true that any P0 algebra can always be deformed. In general, there's obstructions. And indeed, these take the form of anomalies in quantum field theory. But if you can sort of handle those anomalies, maybe you can make them just vanish, or you can trivialize them in some way, you can then produce a BV factorization algebra. So a quantization of this factorization algebra here. And that quantization we call the factorization algebra of quantum observables.
This works for any dimension of manifold?
Yeah, this is like a very universal statement. The dimension's not important at all. Yeah, so any classical field theory on any manifold has this structure here. Doesn't matter, yeah. Doesn't have to be topological or anything, it's just, yeah. Is that your question, or yeah? Yeah, so independent of dimension. Here's an example, though. So topological QFTs, these yield very special sorts of factorization algebra. They're called locally constant. Locally constant means that, that doesn't, if I have two, say, balls, say R to the n, V is also R to the n, and I have an embedding of balls inside of, say, U inside of V, this is maybe they're both inside some big ambient manifold M, your spacetime. Locally constant means that the value of the factorization algebra doesn't depend on the size of those balls, basically. So it means that I have an induced map at the level of the factorization algebra from the value on U to the value on V, and I want this thing to be an isomorphism. That's what locally constant means. This is a version of being topological. So certainly all the topological field theories that Witten would have said are topological satisfy this property here, being locally constant. And there's a nice theorem on locally constant factorization algebras, at least on simple, the sort of model manifold M is R to the n. These are modeled by what are called EN algebras over the operative little n disks. This result goes back to Jacob Lurie. And this is really where this Witten descent is happening here. So EN algebras is like this sort of mathematical incarnation of Witten's topological descent of a TFT. Here's another example. This is the sense in which BV quantization recovers everything you care about in quantum mechanics. So I said that BV is like a sort of universal version of deformation quantization. It's in this sense here. So if I start with a symplectic manifold, of course, then I can contemplate as deformation quantization. How do I phrase this in terms of factorization algebras? Well, the theorem is, and this goes back to the work of C. Lee and Ryan Grady and Chin Lee, that there's a one-dimensional locally constant factorization algebra called OBS with the following properties. So first, when I take its associated graded or take H bar to 0, I get the classical observables that I talked about before. These are equivalent just to functions on the symplectic manifold. This is a P0 factorization algebra by construction, this main result of Costello and William. And it's equivalent to, in this case, just an ordinary Poisson algebra. So this equivalence, of course, does not preserve the sort of bracket here. There's brackets of different degrees on both sides, but there's a little of what's called homotopy transfer happening here between the two structures. And when we BV quantize, we're exactly modeling deformation quantization. This is the statement of the result that I wanted to phrase here. So the quantum observables are equivalent to the deformation quantization of this original Poisson algebra. So BV quantization exactly reproduces Moyal deformation quantization in this sense. It's not the way that, it's a much more complicated way of handling Moyal deformation quantization. I'm just saying factorization algebras can do it. I'm about to use factorization algebras for theories that we don't have such easy methods to quantize. Any questions so far?
And the shift of degrees, what is it? Is that there's some homological degree on the PV side there.
Yeah, exactly. I mean, one place.
That equal sign is on the nose or equivalent on the nose or something?
No, yeah. So this is just like a homotopy equivalence, and I'm saying, yeah, there is a bracket on both sides here. It's just the bracket on this side is shifted, and the bracket on this side is not. So the way to recover this one from this one involves some like homotopy transfer. There's some like degree shifts that happen.
They're just degree shifts.
Yeah. That's right. Yeah. Like what's going on here is like you're basically fixing like a bump function, more or less, like a sort of a bump one form that represents the delta function on the real line. And that's a one form. That's exactly the sort of shift that's happening. It's a shift by cohomological degree one. That's like what's happening here. Maybe one more example that I wanted to say is that sort of really important for me will be the theory of factorization algebras on C. So the complex plane, which are specifically not locally constant. So they don't come from topological field theories, but they come from conformal field theories. And in complex dimension one, of course, that's the same as being holomorphic. There's a notion of holomorphic factorization algebra. I don't want to go into details what I mean by that, but it's not so hard to define. And in fact, there's a correspondence between holomorphic factorization algebras and vertex algebras. This goes back to sort of Bailenson and Drinfeld and all the sort of pioneers of the theory of chiral and vertex algebras. Specifically, the model of factorization algebras that I'm talking about, this correspondence was developed by Costello and William, but sort of it goes back to the heydays of chiral algebras, this correspondence does. So, I mean, this is really where the word factorization was first used, in fact, was in this setting. So using this correspondence between factorization algebras and vertex algebras, we get a really nice statement involving the chiral boson. So back to this 1 comma star forms on a Riemann surface with the BV structure I told you about, namely given by the holomorphic de Rham operator. The BV quantization of that structure, this gives a holomorphic factorization algebra. And the corresponding vertex algebra is exactly the chiral boson vertex algebra that I wrote down in the first slide. I'm not going to go through the details of that, but hopefully you believe me. So I haven't done much. I'm just saying there's this more flexible object called a factorization algebra that is sort of modeling the chiral boson. The other thing is I can invariantly represent the stress tensor as a local Noether current on this space of fields right here. How does that work? So the currents here are labeled by vector fields. That's what conformal symmetry is in complex dimension one, right? Holomorphic vector field. So the question is, given a holomorphic vector field, what's the associated current, local current on this space of fields? It's given by this right here. So remember, B was a holomorphic 1 comma star form. The quadratic term that I wrote down before in the stress tensor in this local form looks like this. So I have a 1 comma star form I can contract it with a vector field to get a 0, star form, and then I can wedge it again with a 1, star form. And overall, this is going to give me some, I just pick off the part that I can integrate, so the 1, 1 component of that object. And this next one's not going to be so important, but so I just won't explain it. But it's very easy to sort of write down the invariant expression for the stress tensor in terms of the field B. So I wanted to point out a sort of another nice geometric interpretation of this chiral boson vertex algebra. And it's related to this Jacobian variety of the curve. So remember, the Jacobian of a curve is h1 of sigma with real coefficients modulo h1 with z coefficients. The way to think about this geometrically is as the moduli of complex structure on the topological trivial line bundle on sigma. So just it's like the 0th component of the Picard variety. And there's a natural isomorphism of the tangent space of this Jacobian variety, say at a fixed complex structure del bar, with the h0 of this complex that I've been working with. So the right-hand side is nothing but the degree 0 fields of this chiral boson theory. So what we obtain from this is that the chiral boson is naturally a family over the Jacobian variety. When sigma is compact, we get a line bundle over J of sigma. This comes from just looking at the conformal blocks of the chiral boson VOA, which in terms of factorization algebras is called the factorization homology. So what we get by studying this in families then and looking at, say, a global curve, like a compact curve, we get a partition function, which is naturally a section of this line bundle. So it's at this point that I want to sort of, I mentioned this as like a sort of stepping stone to higher dimensions. Because the chiral boson, with its relationship to the Jacobian variety, I'm going to sort of start the other way around. Now I'm going to start with a very natural generalization of the Jacobian variety and come up with a higher dimensional vertex algebra which models it, which is controlling it. And that generalization is called the intermediate Jacobian. So the intermediate Jacobian is defined on any odd dimensional complex manifold. And what you do is you look at the middle cohomology. So here, let me take X to be a threefold now, complex dimension 3. So you look at the middle cohomology with R coefficients, and you mod out the middle cohomology with Z coefficients. So exactly the same as we just did for the Riemann surface case. In general, you look at like I said, you just look at the middle cohomology modulo this lattice. So this is called the intermediate Jacobian variety. From the point of view of complex geometry, if you like, so you remember before we had this sort of way of understanding the Jacobian variety in terms of complex structures on the topological trivial line bundle. There's an interpretation here as well, but it involves, as no surprise, gerbs. So one way to think about this intermediate Jacobian variety is as complex structures on the topological trivial holomorphic 2-gerb. So we've actually jumped up 2 in the gerb direction here to say this. We started in dimension 1, we had line bundles, now we're talking about 2 gerbs. So that's one way to understand this moduli space here, is as complex structures on the topological trivial holomorphic 2-gerb. And that's a really good spot if you have some familiarity with M theory, that we're getting at something sort of plausible that should be related to fivebranes. I'm not going to get to fivebranes for a little while longer, but that's a nice hint. What's also very nice is that associated with this moduli space is a higher dimensional version of a vertex algebra. In the same way that the associated to the intermediate or the ordinary Jacobian variety produced this very natural chiral boson vertex algebra. So one way to see that is to, again, look, I'm going to work sort of perturbatively. I'm just going to look at the tangent complex at a fixed complex structure of this intermediate Jacobian variety. And in complex dimension 3, it turns out to be modeled by the coherent cohomology of the sheaf of closed 2 forms with a shift. This comes from the theory of holomorphic 2-gerbs, if you like. So the right-hand side is basically a sort of perturbative version of what's called a Dolbeault cohomology, if you've seen that before, but if not, that's okay. So this expression here motivates the following ansatz. I'm going to invent a field theory on a complex threefold whose space of fields is the same shift of the sheaf of holomorphic closed two forms on the threefold. So the shift amounts to just saying in degree -1, I have 2, 0 forms. In degree 0, I have 3, 0 forms. And then I have all the Dolbeault descendants as well, just extending all the way to the right. So it's if you like, it's the model for closed two forms that I'm using here is like a truncation of the full de Rham complex. So I'll call a field in here beta. There's actually a natural BV structure on this theory, lo and behold. It's very similar to before. So remember, I'm going to search for one which is actually linear. I have a nice vector space here, so I can look for a linear Poisson structure. A linear Poisson structure will correspond to an operator from the sort of left truncated version of the de Rham complex to the right truncated version of the de Rham complex. This is again just by Serre duality. So if I take the linear dual of this complex here of 2 forms and 3 forms, I'll see a complex built from 0 forms and 1 forms, right? At the level of this Serre dual. And that's what I mean by this complex. So the 0, star forms which are of holomorphic type less than or equal to 1. No, it doesn't have to be Clavier, actually, just an arbitrary complex threefold. Yeah. So I'm just saying, if I look at the Serre dual of this complex here up to some cohomological shifts, I just get this complex for closed two forms here. Did you see what I mean? Or, yeah. Might as well, yeah, yeah. Oh, so this, I didn't write it. This is the holomorphic de Rham operator that's appearing here as well. Yeah, exactly. So this is the complex I'm looking at here. This is a resolution for the sheaf of closed holomorphic two forms. This is a nice exercise. This is basically, this follows from the de Rham theorem. Not sheaf theoretically, no. So de Rham's theorem says that. Yeah, you see what I mean? Yeah, so everything's as like a sheaf. So this is as a sheaf, this is a quasi-isomorphism as sheaves. In the derived category, these are the same. Does that make sense? Okay, so we had this Poisson structure, and this actually means, I didn't do this before, but it means we can write down an action functional, almost. The whole problem is that this Poisson structure involves a differential operator. So typically in most classical field theories we study, the Poisson structure is just a constant coefficient differential operator. Sorry, order 0 differential operator, meaning it has no kernel or, I mean, typically it doesn't have, it's just an isomorphism usually. It's a symplectic structure. It's a shifted symplectic structure. That's typically what ordinary action functionals are described by. But because we have this more interesting degree 1 differential operator, the corresponding action functional is actually non-local. And you can write it in this way. So here, I could have wrote this in dimension 1 as well. It's the same formula as before. So let me just do it that case for a second. So remember, B was a 1, 0 form. And that's exactly something I can get. I can obtain a Lagrangian from in that case here, if I interpret this del inverse appropriately. I can do that on a Riemann surface because every 1, 0 form is locally exact. This is just a dimension count. Why can I do this in this case? Well, beta, that's a that's a closed holomorphic two form. And again, by the Poincaré lemma, locally, I can always find a primitive for it. So closed form locally is always exact still. So I can still find a primitive here, which I'll call del inverse of beta, and then I can integrate after again applying del bar and then wedging with another beta. So I get this non-local looking free action functional, which controls this higher dimensional version of the chiral boson. Yeah, you have to take into account of that. So you have to, this is not a well-defined action functional. It's only defined up to some terms. The way to encode that is exactly using BV. So I never actually use that point of view. This is just sort of a heuristic that I'll write down. The way that this is actually handled rigorously is using this BV formalism. So I have this shifted Poisson object, and I can study its quantization. That's what I have. So we do that. And here's maybe some context as well for where this object come from. It looked like I just whipped it out of a hat, but the word gerb did appear, so maybe it's relevant to something. And what we show is that this theory is actually the holomorphic twist of the 61,0 superconformal theory called the tensor multiplet theory. So in 1,0, there's like two sort of superconformal multiplets. There's like the hyper, and then there's the tensor. This is the weird one. This is the tensor. In the physical theory, the tensor multiplet has a very important field called a chiral two form. And the point is that beta here is what survives of that holomorphic, or of that chiral two form. So somehow, Witten very confusingly called it a chiral two form, confusing just for me because I study holomorphic field theory. He called it a chiral two form. There's no complex structure around it all. Chiral just meant its curvature is self-dual or anti-self-dual. For me, I'm calling it the chiral boson theory. There's no anti-self-duality anymore. The dependence on the metric totally dropped out. And this version of being chiral exactly became the condition that your holomorphic two form is closed. So that's the sort of piece that survives this holomorphic twist here. And by the way, everyone who understood the 60-10 theory would have also said there's no Lagrangian formulation in this sense here. So this is compatible with how people think about the 1,0 theory. There's not a Lagrangian, but at least there's this sort of non-local version of it that we can get our hands on. I never actually need to do that because I'm just working with factorization algebras. But... Okay. And maybe I didn't say it here, but we also produce, there's basically a unique quantization in this case as well. So there's a unique factorization algebra of quantum observables here. No. So what I meant was, it doesn't give it to you for free, but in the 1,0 tensor theory, I'm going to get this wrong, but I guess what are your bosons? Your bosons, you have this chiral two form, and then you also have some like pieces of the hyper as well. Yeah, exactly, yeah. So what I'm saying here is that beta are the components. Sorry, beta encodes. Let me say it like this. So beta has remember, it was a closed two form, but with the shifts, the stuff that's in physical degree 0 is a 2,1 or a 3,0 form. And what I'm saying is that these fields here in my model are what survives from the curvature DC in the twist. So really, I'm just modeling the curvature here. So it's particular components of the curvature of the chiral 2 form that I'm finding in the holomorphic twist here. Yeah. All the other components somehow just are BPS trivial, are just are just trivial in this twist here. They just go away. Yeah. Yeah, so yeah, it's literally the thing I'm writing down is really it's a theory of the field strengths and not of the actual potentials. But that's sort of better anyway. Those are more invariant quantities anyway. Okay, so now I wanted to get to the punchline of the first part of the talk. It's about symmetries of this very, very simple. I'm gonna keep calling it a free theory, even though the Lagrangian is non-local, but it behaves in all intents and purposes as a free theory. And the symmetry I'm going to discuss is that by holomorphic vector fields. And this is not a surprise. Closed forms on a manifold clearly have a symmetry by holomorphic vector fields. The question is, can I write down Hamiltonians for that symmetry? That's the hard part. And I need those to be Hamiltonian with respect to that BV structure that I was contemplating from before. In other words, I need this symmetry by holomorphic vector fields to be compatible with that action functional that I wrote down before. Oh, there's no self-duality anymore. Yeah, there's no self-duality here. Yeah.
Otherwise, even though there are a number of different things.
Yeah, maybe I could say it differently. So I think I am sort of lying, and I think some of the bosons from the hyper do sort of make an appearance in here. Yeah, so self-duality is basically being sort of becomes this condition of closedness in the holomorphic twist. That's like roughly what I'm trying to gesture at here. There's no dependence on any metric at all, though. So it's just all I have in the holomorphic twist is a complex structure. I don't have any metric anymore. And del closed. Yeah, so I had both. I had both here. So there's del bar, which is acting internally, and this is the del operator here. Yeah, so that's really what saves you when comparing degrees of freedom, which I'm going to mess up if I do this on the spot. But the fact that it's not just any 2 form, but it's closed is really the crucial thing. From the point of view of the action functional, it's also crucial to even write it down. I need it to be closed to even make sense of this expression. So how do these holomorphic vector fields act? Maybe I can just jump to the punchline. The Hamiltonian are almost the exact same expressions we had before for the stress tensor. So now I'm given a holomorphic vector field. I'm going to model that by 0, star form on the threefold, which values in the holomorphic tangent bundle. And I can find an explicit current, which is also quadratic in the field beta. That's this closed holomorphic 2 form. And this is totally parallel to what we had before. I have to admit there's a slight caveat here because I'm imposing the condition that beta be closed homotopically. There's actually some L infinity terms you have to write down to really get a true Hamiltonian and not just like a Hamiltonian up to sort of on shell. This is all this is accomplishing here is to basically lift this on-shell Hamiltonian to an off-shell Hamiltonian, which is what I always need to do in the BV formalism, but it's not that important. So I just want to point out that given a holomorphic vector field X, I have this, sorry, this should be a mu over here. Mu, I have these Hamiltonians. You can see that this also is something that can be integrated if we just count the holomorphic form type. Let's just say beta is a holomorphic 2 form here. So beta and beta, that means I have 4 holomorphic directions here. But I'm only on a threefold. If I contract with the vector field once, I get 3 holomorphic directions. So it's something I can definitely integrate.
bottom line has a I2.
Oh yeah, so these are L infinity terms I have to turn on here. So, yeah, exactly. So, the quadratic terms will always give me the linear pieces of my action. So just like it did in complex dimension 1. Like this encoded just basically the Lie derivative, how vector fields act on holomorphic forms. But I'm saying that only does that here up to homotopy. So the point is that if beta, let me just say beta is a strictly closed holomorphic 2 form, okay? I'm not doing this, I'm resolving this condition, but let me just say it is strictly closed. Then, and if mu is a vector field, there's a very simple expression for the Lie derivative. What is it? So typically there's 2 terms here, but because it's closed, there's only 1 term. So somehow what this expression here generates is this action here, with this term here in the Lie derivative, which is not enough unless beta is honestly closed. Like if we literally impose the constraint. But I don't want to impose that constraint. I always resolve that constraint. So you have to add more terms here to actually get a sort of consistent action. Yeah. When I write beta, I just mean like an arbitrary. I mean, I'm being a little. So if you count here, it's only the components of beta that look like holomorphic 2 forms that survive here. But in here, a 3 form and a 2 could contribute if I have 2. This is the double contraction. That's what I meant. So I mu. So this lowers form type by 2. This lowers form type by 3. This lowered form type by 1. Yeah.
And also, you also wrote mu is like in the omega 0 comma star. So mu can be not just a global section.
Yeah, exactly. So I'm also resolving that. Yeah. But that's good because this actually gives you more information. It tells you like, what does it mean to work in a background of a complex structure here? It's like taking mu to be some Beltrami differential. That's like a 0,1 form. That's like a Mara-Cartan element in this Lie algebra. And the way to work in that background would just be to specialize all of these all these functionals here at that particular mu. So it's encoding not just the sort of symmetry part, but it's also encoding deformations. That's what is accomplished by looking at this whole complex here. Okay, that was the first part of the talk. So where's this Virasoro algebra? I'm building up to this higher Virasoro algebra. So we just saw that this assignment, given a holomorphic vector field to this stress tensor, this higher dimensional stress tensor, this defines a Hamiltonian action of the sheaf of holomorphic vector fields on this thing I'm calling the higher dimensional chiral boson, this thing built from the closed holomorphic 2 forms. This is all classical. What happens at the quantum level? Well, something happens which is exactly parallel to the ordinary CFT case. Namely, it's not literally the Lie algebra of vector fields which is acting, but only a central extension. It's a function on the fields. Yeah. So I'm calling it sort of a local Noether current. So it's a functional of the fields, which depends on a symmetry. So for every symmetry, you have a function on the fields that's called a Hamiltonian. Yeah, exactly. This is a moment map. I should have said that. So I want to quantize this moment map. Yeah, it generates the Lie derivative action of holomorphic vector fields. Yeah. What I said before is that it's obvious how to define the Lie derivative. What's not obvious is why this is Hamiltonian. So the formulas I was writing down was me sort of lifting the action by Lie derivative, the obvious action by diffeomorphisms, to a Hamiltonian action. So there turns out to be an anomaly to quantizing this action. And here's the way to characterize these anomalies. It's governed by some cohomology group. These are cohomology of the sort of functionals you were just talking about, Hung.
On the space of like field.
I have a shifted Poisson structure, so it's Hamiltonian for that shifted Poisson structure. Yeah. Yeah. Oh yeah, please. Yeah, like when I say Noether current, I mean a Hamiltonian action which is sort of local in the sense that it's given as like an integral over the fields. So that's like Hamiltonian is just like I just mean like find a moment map. When I say Noether, I mean like it comes from an actual sort of like local functional or like local construction on the space of fields, which all of these were. These were all given as like integrals over the threefold of some fields. Yeah, so that's why I'm calling them like currents, because they're these local, they're like manifestly local expressions in the fields. Yeah. So in general, the anomaly to having a symmetry by holomorphic vector fields in any dimension is controlled by this cohomology group here. And I don't want to get into too many details of this. Let me just point out some features here. So X here is any complex manifold that is playing the role of spacetime. N is the dimension of X as a complex manifold, complex dimension. What is appearing here, Wn, is the Lie algebra of formal vector fields. So those are vector fields on the formal N disk. And GF stands for Gelfand and Fuchs, which were the first to study the Lie algebra cohomology of formal vector fields. When I say Gelfand Fuchs, this is like an infinite dimensional Lie algebra, so you have to be careful about what your cochains are. You take those cochains to be continuous cochains. That's what I'm calling Gelfand and Fuchs cohomology. Let me just unpack some very basic versions of this. So let me just work on affine space for a moment. So X is just C to the N. Then anomalies are the dependence on the manifold X just drops out just by de Rhomis theorem. So anomalies can directly be understood just in terms of this Gelfand and Fuchs cohomology. But this was computed ages ago. You can identify the appropriate degree cohomology with certain universal characteristic classes. This definitely has the flavor of an anomaly formula in physics. Anomalies are generally given by integrals of certain characteristic classes. In this holomorphic setting, you see these sort of universal characteristic classes. So what happens when n is 1? I'm telling you the anomalies should be H3 Gelfand Fuchs cohomology of W1. Don't worry so much about the 3 here. So this general result of Gelfand and Fuchs identifies this with H4 of BU1. That's one-dimensional. That's good. There's a unique central extension of the vector fields. And from the Riemann-Roch point of view, it's exactly governed by this characteristic class here, C1 squared. So the corresponding anomaly exactly gives the usual Virasoro or Weil anomaly in this case. And there's an explicit representative for this characteristic class here as a local functional. It's this. J here is the Jacobian. Does anyone remember how many derivatives the Virasoro extension has? That's 3. So J is the Jacobian. There's 1 derivative. That's 2 derivatives. And then del, that's 3 derivatives. So this is, if you unpack this, this is like a more invariant way to write the Virasoro cocycle.
What is mu here?
Mu is a holomorphic vector field. It's a vector field, yeah. So if I take mu to live on C star, I'm saying this formula right here exactly recovers the Virasoro cocycle.
So what's the J?
Jacobian, different Jacobian. No, it's a function. J of mu is, so if we're in n dimensions, this is a GLN valued function. And if mu is a Dolbeault form, it's a GLN valued Dolbeault form. So I just mean it's this thing, di mu j as a matrix. No, it's a function. So mu, I'm writing as mu I di. Then the Jacobian is a matrix valued function whose ij component is dj mu I. Is that okay? So yeah, these are all functions here. There's no one forms around. If I'm resolving, if mu is actually a zero, like a Dolbeault form, then these are actually Dolbeault forms. But there's no holomorphic differentials around, is what I mean. It's all like Dolbeault type. It's not so interesting here because this is just there's no matrix because we're in dimension 1. So I don't have to say anything interesting. But n equals 3. So that's the case we're talking about now. Oh, let me say n equals 2 because I wrote a paper about that last year. It's a little easier. When n is 2, the right group to look at here is the Gauss-von-Fuchs cohomology of W2. And this is H6 of BU2. Does anyone know the dimension of that? It's 2-dimensional. Yeah. So you have 2 of those. And I wrote a paper recently sort of interpreting, what's that? Sort of showing how to interpret these in terms of the famous A and C anomalies you have in 4D, conformal symmetry. So in a rigorous sense, this algebra that appears here, the symmetry that appears here controls the symmetry in a 4D n equals 1 superconformal field theory at the level of the holomorphic twist. And you can sort of, if you obtained a theory from a 4D n equals 1 theory, you can come up with expressions for the coefficients of these anomalies in terms of the usual A and C coefficients. So that's what I did. But anyway, it's like a very clean result, and I think a really nice interpretation of these holomorphic Gauss-von-Fuchs classes, at least some way that it touches base with physics. Now, moving on to n equals 3, that's the case we care about here. Turns out the space you want to look at is H8 of BU3. That's 4-dimensional. So you have these 4 here. That's what their corresponding local functionals look like. You can stare at those if you want. The feature of all of them is they're all quartic in the vector field mu here. So at the level of central extensions, the way to think about that is that you actually don't have a strictly algebra anymore. You have some L infinity algebra extension, but that's okay.
So there's 3-dimensional, so that's 4 generators, 3-dimensional.
4-dimensional, I believe. Yeah, so this is H8 of BU3. That should just say 4. Yeah. 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 There's a 4. So here's just a very quick computation. You can compute exactly, just 1, 0. Yeah, exactly. And I think this is actually consistent with what people say about the independent anomalies in 6010 in the conformal supergravity literature. There's like, I always forget, there's like 1 A and a few C's, or there's 1 C and a few A's. C is always unique. So I think there's 1 C and 3 A's in this case. The C is always picked out as like the sort of Euler density from the point of view of conformal symmetry. So that's why it's special. But then you also have these other invariants as well. So I think actually from that point of view, it's very nice. It says that the holomorphic twist doesn't sort of miss any information, or it doesn't miss a ton of information, at least because the number of independent parameters is the same, just like it was in 4D n equals 1. So what is the Virasoro algebra? Well, we already said this before. It's an extension of vector fields on the punctured disk. So I'm going to do the same thing now in higher dimension, except now my punctured disk is a higher dimensional punctured disk. The whole feature is that it's no longer affine. Yeah, thank you. It's scary because this is not affine anymore. But this is exactly the whole reason I've been deriving everything, because I should. I want to remember more than just functions on the disk. I want to remember that puncture somehow, and the only way to do that at the level of functions is to look at derived functions or derived sections of the structure sheaf. Here we're looking at not the structure sheaf, but the tangent sheaf. So I look at derived sections of the tangent sheaf. That's modeled, of course, by Dolbeault forms with coefficients in the holomorphic tangent bundle. This is a DG Lie algebra. It's just a resolution for holomorphic vector fields on the punctured end disk. And the anomalies that I wrote down before correspond to central extensions of this infinite dimensional Lie algebra. So let me call this non-centrally extended version WIT in analogy with the one-dimensional version. Any one of these cocycles that I wrote down before determines a central extension. That's what I'm saying. So they were classified in dimension n, if you remember, by this certain space of universal characteristic classes here. So of course, when n is 1, we get a unique central extension, but when n is bigger than 1, there's multiple things we can mean by the Virasoro algebra. No, there's not a unique Virasoro algebra, but there's one associated to every one of these central charges. The way to get those, the way to sort of explicitly write down these central extensions is really simple. You just take these sort of formulas I wrote here and don't interpret them as like local currents, just interpret them as residues. And then you get these, you get this central extension here. Z, the residue at z equals 0. Z is the coordinate on c to the n, yeah, on this. Yeah.
Do you really mean some sequence, or do you mean heuristically you took some element?
Oh, I'm just indicating this is a central extension of Lie algebras. That's all. So what I'm not sort of being clear about maybe is that there's a map from what I was calling anomalies to H2 of WIT n. And this is basically the formula for this embedding is basically just take the residue as z equals 0. Yeah. So in particular, any one of these anomalies labeled by a characteristic class gives me a central extension. This is only in a derived sense because you notice that everything I wrote down when n is 3, it didn't look like something which was quadratic, right? They were quartic. But that's fine because this is a derived object. So I mean like total degree 2, meaning that these things don't have to have like uniform polynomial degree. They can have higher degree. And in fact, there's the representatives I wrote down before were all homogeneous of order degree 4. So using our result from before, we obtain the following theorem. So the result I'm referencing here is this statement that the holomorphic twist of the 1-0 tensor multiplet theory is this very simple holomorphic theory. So here's the consequence from of the previous discussion now. The space of local operators in the holomorphic twist of the 1, 0 superconformal theory is a representation for this higher Virasoro algebra, where the central charge is taken to be that formula that I wrote down before that I didn't explain. But you can compute you can compute this anomaly using Feynman diagrams or an index theorem, however you want to do it. It's this class right here for the chiral boson. So using this specific value of the central charge, we get a specific Virasoro algebra, and I'm saying that the space of local operators is a representation for that. That's a consequence of me writing down those Hamiltonians and quantizing those Hamiltonians carefully. That's a consequence. This theorem is a consequence of that. And more specifically, we actually find that it's of a vacuum type. So it's something that should have a higher dimensional vertex algebra structure, which I'm not going to get into today. But the representation we find is sort of very indicative of vacuum representations that you see in CFT. It's very similar. We compute this representation. Well, we compute the character of this representation as a representation for this Virasoro algebra. And one thing we show is that this character recovers the supersymmetric index of this 60 theory on the following 6 manifold. So this is the partition function on S5 cross S1, encodes this, what people call the supersymmetric index. So that this character the character of this object recovers this partition function. So in this sense, we've sort of categorified the index in that sense. The space of local operators is a rich categorification of the index. It's rich in the sense that not only is it a vector space, it's a representation for this very interesting higher dimensional Virasoro algebra. Where did the symmetry come from? Like, why was I able to prove that? You know, I just sort of by hand, I showed you these Hamiltonians, and that's how I got this result. Where did those Hamiltonians come from? Why did we have this symmetry? That's explained by the following result that I recently proved with Fabian Hainer, Surya Raghavendran, and Ingmar Saberi, which describes the holomorphic twist of the supersymmetric object, which encodes superconformal symmetry. This is called the Weil multiplet in a physical theory. So if you have a superconformal algebra around, there's an enhancement of that superconformal algebra to a multiplet. It's called the Weil multiplet, typically, I think. And you can contemplate the twist of that whole multiplet. And what we find is that that multiplet, after twisting, is equivalent to holomorphic vector fields. So this theorem is no surprise in the following sense that, you know, what does it mean to be superconformal? It means we have Hamiltonians for the Hamiltonians for this Weil multiplet. We know how the Weil multiplet is acting. And then I just take the holomorphic twist of those Hamiltonians and I exactly recover the Hamiltonians that I wrote down. So I'm only stating this on flat space right here, C3. It'd be nice to do this in more general backgrounds as well, but this is just a flat. I just want to point out this is a flat space statement.
Are we working on the quantum level or classical level?
This is a classical statement the way I wrote it. The only the sort of quantum statement I have, maybe the strongest version I have is what I was telling Nina before, is that you know, there's anomalies for superconformal structures before twisting, and it turns out that there's a 4-dimensional space of independent anomalies there, which is exactly the same number of independent anomalies I have after twisting as well. So we never actually directly understand like the twist of the quantum Weil multiplet or something like that in a particular theory. We've just done this classically. Yeah.
Do you understand it as an algebra?
So I understand it in many different ways. So one way I can understand it, so the most general way I can understand it is as a factorization algebra. It's a factorization algebra on C3. The way I get an algebra, it's huge. Yeah, it's very big. But one way to get an algebra out, and the way I'm getting an algebra out in this setting here, is to not look at, this is why I was looking at the puncture, it's to look at C3 minus the point. And then you can push forward down to R plus here, just by the radius. So for these holomorphic factorization algebras I start with, if you sort of compactify along this 5-sphere, the resulting factorization algebra you get is locally constant. So that means it's just an associative algebra. So that's where these algebras are coming from. The way I was getting the statement about local operators is a very familiar picture in the state operator correspondence. So, you know, you can think about the vector fields that are supported here as like being supported on a 5-sphere, and they're acting on the local operators here. So that's why this algebra I get out is acting on local operators. Yeah. Did that answer your question? Okay, I'm going to make more. I'd say it's very explicit. Yeah, yeah, it's very, very explicit. Yeah, yeah. That's why I've been sort of annoying and like writing down all these explicit models in terms of like Dolbeault cohomology and stuff. Is like you can really get your hands on this explicitly. Yeah, yeah, yeah. You can just write down generators relations. All right, so I want to turn to the last part of the talk now. Sorry, I forgot to change my watch, I think. Is it? Oh, so I gestured at this before. So this thing should have the structure of, not evaluating on C3 minus a point, but if I just look at it on C3, it should have the structure of like what I want to call like an E3 vertex algebra. And by that, I mean like a vertex algebra where there's like obviously 3 holomorphic directions. So it's just laziness on, because I would know how to do this, but sort of just writing down rigorously what the axioms of such a object is has not been done fully. So it's absolutely, yeah. Just like sort of spelling out what the axioms are and doing that carefully hasn't been done yet. Yeah. We have the objects though. Yeah. That's why I'm saying things about algebras and representations, because I can just like, I can sort of extract from this complicated data of a factorization algebra some like concrete representation theoretic structures. That's what I'm doing. But it should be much richer if we really understand how to codify this whole 3-dimensional vertex algebra thing like efficiently. Yeah. I have like, it's 3:30. Okay. So I want to move on to fivebranes now. It's at this point where I'm going to try my hardest to be a physicist for the last few minutes of the talk. So the theorem of fivebrane, hopefully we all know, is supposed to be an n equals 2, 0 superconformal theory. And I'm going to be, as always, considering the holomorphic twist of this thing. That's what I'm going to try to do. One way to access this holomorphic twist is to actually understand first the holomorphic twist of M theory. That sounds much harder, but the twist of at least 11D supergravity is sort of tractable. And I worked parts of this out with Ingmar and Surya as well. And we found that the twist of 11D supergravity can be placed on any 11 manifold of the following form. So you have one topological direction, which could be a circle or real line. And then all the meat is sort of happening in this remaining directions, which turn out are forced to be Claudia. And on this geometry as well, we write down an actual field theory, classical field theory, which we conjecture is the twist of 11D supergravity on this background. And we give a lot of consistency checks for why this is true. On C5, it's more or less a theorem. I'm not giving you the description here. I'm just telling you the geometry that it exists. It knows something. It's actually quite complicated. So solutions to the equations of motion on this background don't just preserve this product. You actually find sort of deformations not just of the complex structure or of the smooth structure on this piece. You find deformations which sort of mix those two together in a sort of interesting way. It goes under the term of topological holomorphic transverse holomorphic foliation. But let me not say too much about that. For studying twisted fivebranes, one sort of very symmetric geometry to consider is the following. So this all has to do with choosing the Calabi 5 appropriately. The real direction doesn't play a role so much here. It will when you're talking about M2 branes, which I won't. So here X is an arbitrary threefold. Doesn't have to be Calabi. And I guess I fixed a square root of its canonical bundle. And I've looked at this total space. The whole reason for me looking at this total space here is that it's a local Calabi. So I have this is a consistent background to study the twist of 11D supergravity. The twisted fivebranes will be wrapping the 0 section here. So they're very easy from this presentation where the fivebranes are living. So in this geometry, one thing we make sense of is the following. We make sense of the twist of the theory on the original fivebrane before doing this twisted supergravity background. And it has the following space of fields, which you'll find quite familiar. So it has even and odd fields because this comes from a supersymmetric theory, a very supersymmetric theory now. So the even fields, the sort of bosons, are exactly this thing I was calling the higher chiral boson from before. So these are the closed holomorphic 2 forms.
So if I give you just any Calabi 5-fold, and I give you some complex dimension 3 submanifold, the normal bundle always characterized by this, or this is like a special case?
No, this is a special case. Yeah. You know, Yeah, I wouldn't say it's like the most general local model, but it's like, no, it doesn't need to be. Yeah, it's pretty general. I would be, yeah, I don't think these are always locally, yeah. So this even part was the chiral boson from before, and then there's also some odd sections as well, odd fields as well. One way to, if you're familiar with supersymmetry, you can sort of make sense of both of these lines as twists of particular 1, 0 theories. I pointed this out, how this was a twist of the 1, 0 tensor theory. The bottom line is the twist of the 1, 0 hyper theory. So it's even true before twisting that the 2, 0 abelian theory is just a hyper and a tensor. So this remains true after twisting as well. So I'm doing something very similar from before. I'm just throwing in some more odd fields. Exactly, yeah. This is all of the single M5 brane. Yeah, yeah. That's right. So what's the super extension of holomorphic vector fields which is acting now? So, you know, what I mean is that before, the 1, 0 theory I was considering before, we wrote down some currents for holomorphic vector fields, which were the sort of universal symmetry for this piece. I can do the same thing here, right? Vector fields are still acting here. It's totally fine. But now I want to ask, you know, because I have so many more fields, there's more symmetries around potentially. What are those symmetries? Can I describe those sort of universally? And that's what we do. So the holomorphic twist of the 2, 0 theory that I just wrote down has a symmetry by the following Lie superalgebra. So the even part has pieces that we know of, holomorphic vector fields. We knew those were supposed to be there. It also has SL2 currents, so SL2 valued holomorphic functions. That's the sort of residual R symmetry that's acting here. I told you with this geometry, I sort of preserved the most R symmetry. It was like the most symmetric background that I could. And because this bundle basically is naturally an SL2 bundle, that's where this SL2 piece is coming from. So that's the bosonic piece. You have vector fields and you have SL2 connections, basically. 0, 1 connection. And then the odd part is darn it. I didn't write the odd part correctly. It's not going to be so important, but I want to make sure. So it's sections of X, 1 forms tensor k. So it's actually a rank 6 bundle. The odd part is not a rank. I wrote it as a rank 2 bundle. I was forgetting there's a copy of holomorphic 1 forms around. It won't be that important. I'll call this Lie superalgebra E36. I'll say why I called it that in a second. I'm not going to write down the full Hamiltonian currents for this, but you can do it. And we write down some explicit currents for this. But it involves some familiar pieces. So remember this chiral 2 form part, we had vector fields. Now the hyper part, that's where all of the SL2 business was happening. So vector fields are still acting, but then also SL2 gauge transformations are also acting on the hyper. Here. So again, why is this happening? It's no surprise. This E36 object that I just partly explained, we show is the twist of the Weil multiplet for n equals 2, 0 superconformal structures.
So you have the beta and phi.
Yeah, those are the, this was the beta from before, and this was phi. It's just it's really just yeah, it's valued in k to the 1/2 tensor C2. Yeah, these are the fields right here. Yep. Mu is the symmetry. Yeah, so mu is the symmetry as before, beta is the field. So this is, I think about this for like a fixed mu. It's a local current which encodes the action of this vector field mu. This is a local current. Well, I mean, this whole thing is actually the local current which encodes the. Yeah, exactly. I just included the currents for mu and a here. I'm not telling you what's happening in this more complicated bit here. Partly because I got it wrong when I wrote it. Yeah, and write down the right space. Exactly, yeah, which I'm sort of writing here in a sloppy way, but there really is a connection here because I should be resolving holomorphic to be looking at Dolbeault, and I should be resolving holomorphic functions to be Dolbeault. So these are really like, if you want to think about it as like a supersymmetric background, this is telling you how to place this theory in a background with like a non-trivial Beltrami and a non-trivial 0,1 SL2 connection. Yeah. So again, this theorem is no surprise because this E3-6 algebra here is obtained from the twist of the 2, 0 Weil multiplet, the thing that's controlling superconformal structures through a 2, 0 theory. So it has to be the universal thing. So Weil multiplet to me is it sort of encodes all of the currents for a superconformal symmetry, the Weil multiplet. It's sort of like the home for all of the superconformal currents. So like the simplest version of the Weil multiplet is called the stress tensor. So it's like supersymmetric versions of the stress tensor. Does that? Okay.
And you're doing a twist.
Yeah. So it exists before it. I wouldn't be able to write it down in a single piece of paper here because it's very, very complicated. But I can write the twist down in a single piece of paper. That's this E3-6 thing. Yeah. So when I evaluate this thing on a very simple threefold, X is C3, that's where this terminology comes from. So it turns out that this algebra here becomes the Lie superalgebra discovered by Katz and collaborators, which fits into, it doesn't fit into one of his families of infinite dimensional Lie superalgebras. So there's like 5 or 6 sort of families of infinite dimensional Lie superalgebras. These are all basically of the flavor of like vector fields on a formal space, possibly preserving some symmetry. It turns out there's like 5 or maybe 6 infinite dimensional Lie superalgebras that do not fit into this classification. And Katz called these exceptional in analogy. Their Dinkin diagrams are sort of very analogous to how ordinary exceptional Lie algebra Dinkin diagrams look. And this exceptional one, he called E3/6. And if I spelled out what was happening before just on X is C3, you'll find his description here. So the even part, you have formal vector fields, and then formal SL2 functions. And then you have this space of one forms twisted by some square root of the canonical bundle with values in C2. I haven't said anything about the brackets are, but if you want, you can think about what the Lie brackets are here. It's sort of clear vector fields are acting on the odd part in the natural way. SL2 is rotating the C2 as a fundamental. The interesting thing is how the odd to even brackets look, but I don't want to say what that is. So here's a consequence. The local operators of the 62,0 theory now in the holomorphic twist are naturally a representation for E3/6. So this is a parallel to that result we had before about the 1,0 version. So as a consequence of this, we get a nice categorification of the 62,0 superconformal index now. So the 62,0 superconformal index, what we prove now is that it's obtained as the character of a particular E3/6 representation. So that's the sense in which this this categorifies the index. Yeah. So Katz exactly classified all irreducible representations for E3/6, and we can say exactly which one it is. Independently verifying what, like. Yeah, exactly. We do it directly, and we find an exact agreement with Katz's. So Katz computed characters for all irreducible reps, just because that's what representation theorists do. And we actually looked at, with some tweaking with his formulas, because he doesn't use sort of physically natural parameters, But when we use the physically natural parameters, we exactly recover our direct computation. But you're totally right. We can directly compute it and just get the answer. Yeah. But Katz did this 25 years ago, like he did everything. So yeah. One thing to point out, though, is that this E36, this was only half of the story, really, because this was just about placing the theory on C3. So it's, from the point of view of the Virasoro algebra, CFT, this is like the positive part of the Virasoro algebra, because it's just about the behavior on, I filled in the point here. I haven't punctured the disk. So we should be actually finding some bigger algebra, which is acting once we puncture the disk and do this sort of state operator correspondence that I was gesturing at over here. And that's exactly going to give us a version of the, it's going to give us a version of the Virasoro algebra. And just like before, once we puncture, there's going to be anomalies around. We're not going to get a representation on the nose. We'll get some projective version for a central extension. And the anomaly is just more complicated in this case, a priori. So there's the bosonic part of the anomaly, for example. It's going to be very similar to before, at least on the vector field part. So we have these universal characteristic classes which will appear. But there's also going to be anomalies involving the SL2 gauge field part as well. Those generally all look basically like this because we're just SL2. It's not much you can do. This sort of anomaly had already been sort of studied by Fayante, Henion, and Kapranov in the context of what they call higher dimensional Kac-Moody algebras. So really inside of this enhanced symmetry is a version of what they call the higher dimensional Kac-Moody algebra. That's somehow just the SL2 part. This is like sort of familiar in ordinary superconformal symmetry, like 2D, I don't know, 2D n equals 2 or n equals 4 superconformal symmetry. Like inside of those are always some nice affine Kac-Moody algebra controlling basically the R symmetry part, right? So this is a version of this, but it's a higher Kac-Moody algebra. But, and Mina was sort of gesturing to this earlier, is that once you have more supersymmetry, you should actually expect that the number of anomalies actually, independent anomalies actually goes down, so shrinks, just because there's more symmetry around. It should be harder to be a cocycle or an anomaly for this Lie algebra. I can't show that there's a unique anomaly in this case. That's our conjecture, is that there's actually a unique anomaly here. And I don't know if this is consistent with conformal supergravity literature or not. I've seen some references which say there's one, and I've seen some which say two. So I'd like to talk to a physicist at some point and tell me which one's correct. But what I can show is something sort of nice, is that the map from anomalies of this full algebra to just the anomalies for the bosonic part, just the even part, is injective. What that means is that to really characterize the anomaly, all I need to do is understand the bosonic part. I don't have to worry about the fermions in an essential way. And here's a nice corollary, which is sort of independent of the rest of the talk that I just want to say because it's really cute. If I look at the holomorphic twist of n equals 2, 0 conformal supergravity, coupled to n M5 branes, I mean n single M5 branes here, so I don't mean a stack of n M5 branes, it's slightly different. So it's just like n independent 5 branes. So if I look at this coupled theory, it exists at the quantum level if and only if n is 26. It's the same 26. That's part of the, that's why I got so confident in what I was doing here, is this is the same 26 as in bosonic string theory. Yeah, maybe I'll explain in the next few slides. Yeah. If I don't, please let me explain. Yeah, because I can explain it. Oh yeah, what I said was, so I take M5 branes, n M5 branes here. It's really n independent M5 branes. So different, I'm not studying like a stack of n M5 branes. Yeah, but I'm doing, the other thing is I'm doing conformal supergravity here. 60 conformal supergravity, not just supergravity. So maybe I can explain one appearance where it comes from. I have some understanding of it. Yeah, I don't have a full string theory understanding. So I was gesturing at all this because I had mentioned before before we found that the local operators were a representation for this E36 thing, but that was only half the story. Once I puncture the disk and take the central extension, I find a version of the Virasoro algebra which is acting, and this is now a central extension of this huge algebra, including all of the even and odd symmetries that I was talking about before. Yeah, dynamical supergravity, yeah.
Oh, no, sorry, then I have a draw question.
Yeah, I just meant like this is like an independent comment. Yeah. Yeah, there's nothing like M theory going on in that. Yeah. No, it was just a nice. Yeah, exactly. Yeah. So you get this huge central extension now that's acting. And this thing includes a lot of interesting subalgebras that I've already mentioned. So it includes the positive part, that's this thing that Katz calls E36. It includes this, actually in the central extension, it includes the higher Kac-Moody algebra for SL2 that Fayonte, Hennion, and Kapranov constructed. And it also includes the sort of higher dimensional 3D Virasoro algebra that I mentioned in the first part of this talk as well. So it has all of these things going on. And from what I've been saying is that this algebra here is naturally acting on the minimal BPS operators in a 62,0 theory. So take your favorite 62,0 superconformal theory, take its holomorphic twist. Its local operators will always be a representation for this very big algebra. We do a little more than just study the abelian case. So we actually were able to come up with a conjecture for what the theory on a stack of 2 fivebranes is, at least at the level of the holomorphic twist. It turns out to be induced from a representation that Katz studied for E36. We compute the character of this both directly from the point of view of the factorization algebra and also using sort of Katz's computations. And what we find is an agreement with state-of-the-art index computations for non-abelian superconformal theories. So what I mean is that we have a closed form expression. There's no closed form expression for the full supersymmetric index of a non-abelian theory, but it agrees like all the way up to whatever order people have actually pushed it to. Our closed formula. Yeah, yeah.
Isn't there the none of the non? You clearly can't capture any of the non-abelian, right? So the non-contributed, is that a thing?
So we don't access at all directly like what it means to be like a non-abelian gauge field at all. What we did was we sort of used our description of 11D supergravity to make an educated guess as to what the factorization algebra is on a stack of 2 fivebranes. But it's not obvious at all how it comes from like the quantization of some like classical field theory at all. So this is very different than the rest of the talk. That's why I'm putting it as a remark. But in any case, the objects we do find are representations still for E36. And their representation theoretic characters agree with however far people can go in this, whatever I guess you would call it instanton number, like as far in instanton number 1 goes in these non-abelian calculations, like we just agree with those results. That's due to some Koreans, Kim, and Lee. I'm just giving one reference. There's a few other references that perform similar computations. Okay, in the last bit, I want to now turn to this sort of AGT story. So when X, remember X was a threefold. When X is a special threefold, if it's a product of a Riemann surface with C2, then there's a simplification of this 6D theory, which is called the omega background in the physics literature. Mathematically, this is akin to taking some equivariant cohomology. So here the equivariant, the group is a torus, S1 cross S1, and it's acting on at least in the twisted setting, what I mean is it's acting on each of these C's by rotations independently. We can make perfect sense of this omega background in the holomorphic twist. It's actually very nice. It turns out to be very, very akin to a process like twisting. And what I mean is that the omega background can be understood as working in a certain E36 background. That is, there's a Mara-Cartan element in E36. That's this enhanced algebra that I was talking about before, the thing that came from the twist of the Weil multiplet in 62,0. So there's a Mara-Cartan element inside of here describing this omega background. And how does this work? Well, I said it's like twisting. So what you do is you take your theory, let's just work with the factorization algebra of observables in the holomorphic twist. And then you literally just deform by this background. You just deform by this element. You work in this background. And what you find is that this factorization algebra, at least for generic epsilon1 and epsilon2, localizes geometrically to the Riemann surface, which sort of makes sense. If I'm looking at the equivariant cohomology here, localization should tell me everything's just happening at the point inside of C2. And that's exactly what this is here. The cohomology, yeah, it's different. It's a different presentation for that, for the equivariant cohomology. That's right. Yeah.
And you're still going to do this here?
This is actually very general, this statement here. So if my factorization algebra admits a symmetry by E36, then this statement is true. Yeah, and the examples I have firmly are the abelian theory. And then I also have this, we have a conjecture for what a theory on the stack of two fivebranes are. And it also works for that too. But those are the only two examples we have, yeah.
So in your Carl Dolbeault story, you can presumably describe a reveal for like flow and gas formula.
Right? Oh, I would love to do that, yeah.
Oh, you should be able to do that.
I know.
To do that, I mean, I think that's
This is my dream. This is my dream lately, actually. Absolutely, yeah. So it's about lifting this free field realization to. This is what I've been obsessed about the past few months. Yeah, yeah.
I'm sure you will.
I hope so. I'm trying to get it to work just for the SL2 theory first, just like. Yeah, yeah. I hope I can report soon about success. Yeah, I don't yet have any. Yeah, exactly. Yeah, so we have evidence at the level of characters that supports what we're doing is correct, but we don't have like a full factorization algebra construction yet. Yeah, I'd like to, but that's a very good question. Yeah. Sorry, it's a very good suggestion. So this localization or background leads to a nice mathematical statement going back to Nakajima and Goniowski, which is that at least when the Riemann surface is just C, that the equivariant cohomology, S1 times S1 equivariant cohomology of the Hilbert scheme of n points on C2 is naturally a vertex algebra. This Hilbert scheme that appears here is nothing but the solutions of the equations of motion that we get in this background here. So it's a particular compactification of the moduli of anti-self-dual connections that you would see from the point of view of Yang-Mills theory. And of course, this result not only says it's the vertex algebra, it identifies this vertex algebra with the chiral boson vertex algebra in the case of C2. And we can see that oh, I meant to actually write on this slide here. We can see this directly from the point of view of factorization algebras as well. So starting with the holomorphic twist of the 2-0 theory, abelian 2-0 theory, performing the omega background, we exactly recover Nakajima and Goniowski's vertex algebra constructions. So we see it just from the point of view of factorization algebras, meaning we don't ever talk about, we don't ever sort of get into the weeds of like, sort of the usual way people construct this vertex algebra is via correspondences on the Hilbert scheme. We see this sort of directly by looking at the factorization algebra associated to the theory. So there's no, what we're doing sort of is morally encoding the same structure that Nakajima and Goniowski use, but it's not clear why.
Statement is the proper factorization algebra, you see that the right one is the highest order.
Yeah.
Whereas like usually this is factorized.
Yeah, exactly. That's right. Yeah, and we know, I mean, we know how to see this space here just from the reduction. So, you know, if we take the reduction of our twisted theory on a circle, we exactly see a twist of 5D Yang-Mills, whose Hilbert space is exactly this space right here. At least after doing this equivariant version, at least. So in that sense, I view it as being sort of a well, nothing here is non-abelian anyway. This is all just abelian. Sorry, when I said AGT, I'm doing just the abelian case for now still. Sorry, I wasn't doing the non-abelian version. This is just the abelian version. Yeah, I'm really sorry. This is just all abelian. So it's like really things we get our hands on. We're not making any guesses right now. Yeah. And then one nice statement about symmetries now, this is not so much of a surprise. What happens when I put this huge symmetry that was acting on the 60 theory in this omega background? You could maybe be hopeful that, you know, we could uncover this huge symmetry that's acting on this vertex algebra. Well, it's not that. It's nothing. It's just the Virasoro algebra. So this just explains this notation that I'm using here. It's sort of this Dolbeault enhancement of this Virasoro vertex algebra. Let me see. Yeah. So I'll just finish by saying some more words about sort of enhancements of this statement here that I'm currently working on. So
you have something factorization algebra on C3 and you do two of the direction you get the factorization algebra on C.
Yeah, like sort of what I was gesturing at here is this process is actually a functor. So you get a functor from like E3-6 structured factorization algebras on C3 down to factorization algebras just on C. That's a really good question. I don't know if you can do that. That would be a good question for Mina. Should you be able to, in the omega background story, should I be able to, so I can actually answer that, yes. So you can take one of these to be, I made a generic statement before, is that epsilon 1 and epsilon 2 are generic. This thing localizes to just a point in C2. But if you take them to be non-generic, say epsilon 1 is non-negative and epsilon 2 is 0. That's like, you should just be localizing like one of the directions. So this should result in some 4-dimensional theory. I think this is where these sort of codimension 2 defects are coming from in 60, but I'm not entirely sure. It seems to be close to that, but mathematically, you can definitely do that. I just don't have like a sort of string theory interpretation of that. I can say some more interpretations of that too. Like another one is that somehow when these are generic, there's a level in the chiral boson, and the level of the chiral boson is like the ratio of epsilon 1 and epsilon 2. And somehow like taking epsilon 1 or epsilon 2 to 0 is like taking a classical limit of the chiral boson vertex algebra, which sometimes has the effect of like smearing it out over another direction in a weird way. This is sort of hand waving, but I can say what I mean more precisely later if you want. But the sort of statement I was making here was generic. So when epsilon 1 or epsilon 2 are generic, you localize to a point in C2.
Aren't you effectively going to get one in the 4-dimensional?
What's that?
Oh, yeah, you'll just get a 4-dimensional.
Yeah, you do just get a 4-dimensional thing. I want to understand maybe at first principles. I'd like to know like what that 4-dimensional thing is from the point of view of M theory or like some string theoretic construction. Yeah. Okay, so the last part I just want to talk about is basically working not with C2 but now with a algebraic surface or a complex surface, which is equally suited for the holomorphic twist. So Remember, X could be any threefold, so I'm allowed to look at this threefold here, S times C. Well, actually, Nakajima already tells us that there's a deformation of this theory, which there's a deformation of this theory whose Hilbert space is the de Rham cohomology of the Hilbert scheme. So here there's no equivariant parameters around because I don't necessarily have any. You just see the full de Rham cohomology of the Hilbert scheme. Again, this is all abelian so far. But you arrive at this by doing some sort of topological twists of the six-dimensional theory, this AGT sort of twist. From the point of view of 5 dimensions, this is like a type twist. It's like a fully topological twist. But what if I didn't want to do that? If I didn't want to perform that additional topological twist, if I just wanted to look at the holomorphic twist? Well, it's not so hard to imagine that what is replaced by de Rham cohomology is the Dolbeault cohomology of the Hilbert scheme. By Dolbeault here, I mean the coherent cohomology with values in the de Rham, holomorphic de Rham complex. So that's really cool. Like we can use this to sort of possibly enhance Nakajima's story, but there's actually no difference at all because when S is, at least when S is proper, Hodge de Rham totally degenerates here. So there's no difference between this Dolbeault and de Rham cohomology. They don't get anything new. I will say one thing is nice is that from my point of view, we actually explicitly see the Hodge decomposition of the Hilbert scheme on S, which is really nice. That's like one thing the holomorphic twist gives you. So that's cool, but it's like isomorphic as a vertex algebra to doing the topological thing. So it's not a new vertex algebra. But there is a way to get some new vertex algebras here. So let me just, and this is work in progress. And this has to do with considering M theory on a slightly more general or less symmetric background. So remember, we have to have an 11 manifold, which is of the form R cross Calabi-Yau. So R is not going to. Oh, yeah, sorry. So right, I'm taking the sum over all K there, of course. But if I wanted to fix K. Oh, so I would look at like a fix, like the subspace of conformal vectors of like a fixed weight or subspace of vectors of a fixed conformal weight is the way I would see that full space. Yeah. But we don't see it like more directly than that. Like that's that's why I'm saying this. That's like the disadvantage of this point of view from the point of view of like correspondence diagrams, for example, where it's like much easier to see where those classes are coming from. So here's this more general background. The R is the same as before, and the Calabi-Yau 5 is of the following form. You could do more general things, as was pointed out to me a little bit ago, but this way works quite nicely for what I'm going to say here. So you take your, let's just say it's a proper surface, and you have a line bundle on that surface. So that's the new data here. It's the line bundle. You look at this rank 2 bundle, which is the total space of the line bundle plus its Serre dual. I did this now because this is, again, a local Calabi-Yau. This thing is just flat. So I just put the obvious Calabi-Yau structure in this, and this is the Calabi-Yau 5-fold that I have. Where's the 5-brane? It's wrapping the base of this total space and this copy of C here. So the vertex algebra is going to live here. So if I want the mode algebra, I would puncture it. If I want the vertex algebra, I don't puncture it. Yeah. But you could do both. Yeah. So then what we expect is that there's a symmetry, which there's a symmetry of this background here, which is playing the role of E36 from before. It's now labeled by the line bundle L. We didn't have a line bundle before. So it's a slightly, I mean, it's very analogous, but it's now depending on L. And what should this be acting on? Well, this should be acting on the solutions of the equations of motion after I reduce my 6D theory down to 5 dimensions. And that solution of the equations of motion have the following form. So instead of looking at the Dolbeault cohomology of the Hilbert scheme, I see the D-bar or coherent cohomology of the Hilbert scheme with values in some bundles. And these are bundles on the Hilbert scheme called tautological bundles, which you can define given any line bundle. So actually for every, I'm being a little sloppy here, for every K, there's a tautological bundle on Hilbert K defined using the line bundle L. And I can then look at the direct sum of all of those. And I haven't seen the statement in the literature, but one possibly new statement is that this cohomology right here has the structure of a vertex algebra. And this hasn't really been, as far as I can tell, studied. The nice thing is that these cohomologies have been studied. So once I understand that well enough, I can hopefully start to make some comparisons of my factorization algebras to some known results about this cohomology of these tautological line bundles. But the algebraic structure, I think, is generally. I don't have anything to say maybe in this setting about that. If S is not proper, I would really be only comfortable if there's some extra equivariant parameters around. Oh, yeah, then you could do the same thing here. So you could take your line bundles to sort of depend on two different weights, and like you could see a version of that's a really nice suggestion. You do the same thing here. So there should be a version of this on C2 if I also take S1 cross S1 equivariant cohomology. I would expect a very similar statement. Yeah. Ah, yeah, I said it in words, but I didn't say it.
For you on C2, what do you mean, like, if we're doing coherent stuff here by equivariance, do you mean either just remembering the usual sheaf cohomology of the module or the?
I think that's what I think that's what you need. No, I think just remembering it as a module, I think, yeah.
So what do you take
Yeah, so it's del bar with coefficients in the de Rham forms. Yeah, that's what I meant by Dole, yeah. I'm done now, actually, so, yeah. Oh, yeah.
The K point on the surface.
Yeah.
It's kind of that empty green part, like the.
Yes, yeah, definitely. Yeah. I'm sorry for going over.